All right, so this last page, it's a chart, and we're going to use our structures that we've drawn to figure some of these out. Okay, so the first one here, we have SF6. So we found that one already. The number of groups on the central atom is 6. Number of lone pairs, 0. This means the electron geometry, so I'm just going to go ahead and write that in. And this means molecular shape, just using the same terminology that I use. Any lone pairs? No. The electron geometry is octahedral. It also tells me the shape is octahedral. And even though these bonds here are polar bonds based on electronegativity, all of these angles being 90 degrees, they're going to cancel each other out. So ultimately, this is not a polar molecule. All right, next one. It's a little bit of mix and match. We are looking for 5 groups and 1 lone pair. So let's kind of look through here. Here we go. 5 groups, 1 lone pair. Okay, so that is VRF5. So 5 groups, or sorry, 5 atoms, 1 lone pair, adding up to a total of 6. So it's octahedral, but the shape is square pyramidal. All right, looking at this, we have a lone pair of electrons and maybe some polar bonds. This is in an orientation where things are not going to cancel out as far as dipole moments. So yes, this is a polar compound. All right, now we're going to be looking for this one. It tells us it's octahedral geometry, so that means there's a total of 6 groups. 4 of them are bonded, which means 2 of them have to be lone pairs. So let's see if we can find that one. So here we go, 4 bonded, 2 lone pairs. This is ICl4 minus. ICl4 minus 1. So this is octahedral. The shape that corresponds to AX4E2 is square planar, sorry. Square planar. All right, so when we do this, in this orientation, we're going to have 4 atoms. These bonds, I'm not sure if they're polar or not, but it's not going to matter because they're all at the same angle to cancel each other out. The electrons are going to be on the top and the bottom. So this is a very symmetrical molecule, and so the symmetrical molecules are generally going to be nonpolar. XeCl3, we've drawn this one already. XeCl3, it has 3 bonds and 3 lone pairs. 3 plus 3 is 6, so that means there's a total of 6 groups, so it's octahedral. The shape for an AX3E3 is T-shaped. And as you can imagine, a T-shape is not going to be particularly symmetrical in a way that's going to cancel things out. So these are polar bonds. And then you have 3 lone pairs. So yes, this would be a polar molecule. Polarity is kind of tricky. I don't put a lot of focus on it. You'll see it more in organic. But next, we want 5 bonds, no lone pairs. 5 bonds, no lone pairs is going to be this one, PF5. All right, so remember when we have 5 bonds, that's trigonal, bipyramidal. No lone pairs means the shape and the geometry are the same. Trigonal, bipyramidal. All right. Now, all of these bonds here, they're polar bonds, but they're at angles that are going to cancel each other out. So this would not be a polar molecule. All right, let's look at the next one. We're looking for 4 bonds, 1 lone pair in a seesaw orientation. Well, we can match up our molecules. So we're looking for an AX4E1. AX4E1, that's this one. It tells us it's a seesaw orientation. So let's fill in the blank here, SF4. We know anything that has a total of 5 groups is trigonal, bipyramidal. Seesaw orientation is always polar. BRF3, let's find that one. Here it is. We have a total of 5 groups, AX3, E2, 5 groups, also trigonal bipyramidal. And this corresponds to a T shape. And with the T shape, polar bonds and lone pairs do not cancel each other out. So this is definitely a polar molecule.